Good morning. We're going to take a quick look at how to go about doing that quintessential retaining wall problem that we've looked at way back in stormwater, looked at in terms of distribution of a triangle distributed load on a number of times. So I'm going to go ahead and just see if I can do it all here. And then what we're looking at is to realize that this problem, when we get done, we want to be able to look at it in terms of a three-force system, even though those forces are the weight of the wall, which acts down. We'll look at this weight of the soil. I'll close that out here. Hit to continue here. That's probably not good. All right, weight of the soil. Cancel here. I don't know why it's trying to do it. RDBMS here. Drawing Transfer Wizard. Wow. Doesn't that look nice? Exit. So who knows how that came up. Alright, that's probably AutoCAD. Weight down and the pressure or stress normal. And the it's going to keep going on me here. Normal is pressure normal, and of course the shear and the reactive normal force will be equal and opposite to those other two. So I'm going to sketch it here. I'll see if I can insert actually a wall for once. Use the tools within here. Kind of draw this wall here, and I'm going to give it a foundation here. And we'll make the foundation a pure toe foundation. Insert a shape, something like this. Kind of make that something like that. And we'll just make that kind of as it is. And now I'm going to go back to review pens. Alright, so we're going to give this height from here to here. And we're going to go ahead and actually, we'll give that a height of 10 feet. We're going to give this a width of 2 feet. We're going to make this a width of 10 feet, and we'll make this 3 feet. And for the simplicity of the demonstration here, so we don't have to deal with too many forces, I'm going to put this before it's backfilled here. And I'm going to tell you that basically the author uses very much, sometimes not uses this kind of simplification of Rankine formula, but he uses basically a gamma effective of something 40 pounds per cubic foot. Now that is not to say that he is actually doing anything about effective stress, but 40, so this is, let me go ahead and use the eraser. I'm going to tell you that the unit weight of the soil, if you would, effective is about 40 pounds per cubic foot, and the unit weight of the concrete we'll use 150 pounds per cubic foot. And what we want to see here, that this turns out to be a three-force concurrent problem. So first off, let's look at what is the free body. Well, the free body is, we're going to show, in this case, this has some sort of contact force. Now we're going to show that as a pressure here, and it's a combination of a pressure that looks something like this, just due to the weight, and something that looks something like due to this, due to spinning about some axis. So this is negative and this is positive. We're just going to show that on some as a reaction force in some direction here, up to and including that kind of coefficient of friction, or mu, the internal angle, I'm sorry, the friction angle. So we have that 10 down, we have 7 here, and so we have this is 3 by 10, so this is going to be for 1 foot out of board. If you remember, we do a lot of things by saying 1 foot out of board. So this is 30 cubic feet times 150, and it acts down at the centroid, which is 5 to the right. This one is 7 times 3, 21 times gamma of concrete. So that's 21 cubic feet times 150. Right? You're going to add these together. These are parallel and they act down. So their resultant is somewhere in between, and it's a weighted average in between. This one here looks like that. It goes from 0 at the top to 400 pounds per square foot. We take the area underneath, and that is the force, and it is placed at 1/3 from the bottom end. Now, if you think about this here, this in effect is going to be mostly, really doesn't have a very high torque, because it's not very high on the wall, especially when you think about these forces here. So the sum of these forces might end up being there, the concurrent point. So that one is 400 plus 0 divided by 2. So 200 times 10 square feet. So that's 200 times 10 square feet. Now you got that, of course, by 1 foot on the ball, so that turns out to be 2,000. And this is what, 1/3 from the heavy end. And so in effect, you have now a process of adding up this resultant and this one coming down, this one coming over, and them having a concurrent point through which this has to be equal and opposite coming back up. So let's look at that in a second vectorially. So let's assign our coordinate system right here, and let's put that force right there. Well, force to the soil is defined as 0 in the x and 3.33 in the y. And its force is 2,000, if I have that correct. And it is 0 in the y, though in effect the Rankine would have a little bit of a force down because of the effects of friction per se. Alright, that's the force of the soil. The weight of the wall is going to have 2 components. One is going to be equal to, it'll be placed at, not at 0, it is going to be at 1 in the x because it's the centroid, and 1 halfway up this wall. So this wall is 7, so it's 3.5 plus 3, it's 6.5. That's where this is placed on the y, and it is down, boy, that's 3,031.50. So it is minus 3150, and it is 0 in the x. I'm going to call this the wall and foundation. And that foundation, of course, is then going to be placed at 5 and 1.5. And its weight down, we said, was 150 times 30. 10 by 3, 150 times 30 would be 4,500 minus 4,500. And of course, this is 0. Now, you can go about using these vectorially. What you need to do is you need to add these two together based on a weighted average. And so what the weighted average becomes is if you think about from here, it is along this direction, which is all we're really worried about for the overturning. It would be 1 times 3150 plus 5 times 4,500, all divided by the sum of the two. So you would have in the end some weight force here. You would have some other force there. You could get your point of concurrency, and effectively what that would get you is this reaction force would be equal and opposite going through that point of concurrency. So that's the effective way how to do these. I will redo this problem with numbers tonight and resketch it, but that effectively is how you go about solving these simplified retaining wall problems. Of course, in reality, you have This force here is broken up into a shear force and a normal force, which acts something like this. They all become actually stresses or pressure. That you have basically bearing capacity of the soil and shear capacity. You might have a, if this is buried, you might have a force coming back the other way, a stress coming back the other way. You might have some soil up on top of here which would act this way and act that way. So there's all kinds of complexity you can get this. But at its core, it's a way to once again apply a mix of graphic and matrix methods. Thanks for listening.